So how do we work with equivalence relations when it comes to math? We are confronted with a mathematical relation. We want to know whether or not it is an equivalence relation. So first, let's look at the more pleasant, easy approach to this. Let's suppose that I want to show that a given relation is not an equivalence relation. Here's what's nice. If I want to show that a relation R is not an equivalence relation, all I have to do is prove that it fails to satisfy any of reflexivity, symmetry, or transitivity. I can do, for any of these, I can do disproof by counterexample. So, for example, here's a relation that we can study. So A related to B means that A is strictly less than B on the set of integers. So here A and B are always going to be integers. So this particular one fails reflexivity. And this is because, for example, 1 is not less than 1. That's not true. And so it follows that 1 is not related to 1. This is a very quick and kind of casual disproof by counterexample. I've found an element of the integers which is not related to itself. This actually also fails symmetry. Fails symmetry. So in particular, for example, two is less than 3, but it is not the case that 3 is less than 2, which means that we have found something that's 2 is related to 3, but 3 is not related to 2. So this is enough, even one of these, I didn't even have to show both reflexivity and symmetry. This is enough for me to show that a relation is not an equivalence relation. I have proven that this relation, the less than relation, is not an equivalence relation. Now, unfortunately, the situation is quite different if we want to show that something is an equivalence relation, because if I want to show that a relation R is an equivalence relation, yes, it is. It's not enough for me to find counterexamples. I need to write 3 proofs. I have to write 3 proofs. So here's an example. Our relation this time, A is related to B, is going to mean that A plus B is an even number. And this relation will also be on the integers z. So our theorem that we want to prove, is that this R is an equivalence relation. And that means that in order to prove this, we need to write 3 mini-proofs inside our proof. Okay, so first mini-proof is for reflexivity. So to do this, I'm going to do direct proofs, and I'm going to do relatively short direct proofs where I'm skipping a few of the mechanical statements that we sometimes make. So my proof of reflexivity is that for any integer a and z, a plus a, which is also the same as 2a, is even, because I've written it as 2 times an integer. So that's enough to have shown the definition of reflexivity. For all a in z, a is related to itself. Now I need to prove symmetry as well. proving that something is an equivalence relation requires 3 mini-proofs. Okay, so now for any a and b in the set of integers, if a plus b is even, then so is b plus a. They are, after all, the same number. That's how addition works. It doesn't matter what order I do it in. So this is a proof, a quick little informal direct proof, that for all a and b in the integers, a related to b means that b is related to a. Okay, last one. We have to prove transitivity. Transitivity is almost always the most challenging part of a proof that something is an equivalence relation. So let's get right into it. Let a, b, and c all be integers, and assume that a is related to b and b is related to c. Then, so now I'm going to use the definitions of my relation here. I know that a plus b must be an even number, so that means it's equal to 2k, and b plus c is also an even number, so it's equal to 2j for some choice of k and j in the integers. I don't know what the k and j are, but I don't have to. Then, and now I'm going to do a little bit of algebra, let's consider what we know about a plus c. That's ultimately what we care about here for this relation. We want to show that a is related to c. A plus c, I'm going to do something just a little bit sneaky here. I am going to write this as a plus b plus b plus c. I added 2 copies of b, so I'm also going to subtract 2 copies of b. That's allowed. I'm just adding 0 to the right-hand side of the equation, 2b minus 2b. Then, if I substitute here, well, I know that a plus b is equal to 2 times k, and I know that b plus c is equal to 2 times j minus 2b. And this is equal to 2 times k plus j minus b. I've just factored out the 2. Therefore, I've shown that a plus c is even, so a is also related to c. So this was a direct proof. Since I didn't assume anything about a, b, and c, I just said they can be any integers. Therefore, I've shown the statement that I wanted to do here of transitivity, which is that for all a, b, and c in the set of integers z, if a is related to b and b is related to c, then a is related to c. So these 3 proofs, I needed to prove reflexivity, I needed to prove symmetry, I needed to prove transitivity, and I did each of them in kind of a short, casual fashion. These 3 proofs are all necessary. If I want to prove that something is an equivalence relation, I need to do all 3 of them: reflexivity, symmetry, transitivity. On the other hand, if I want to show that something is not an equivalence relation, I only need to do one thing. I just need to find at least one counterexample for one of these properties. Y'all, in this video, we're going to prove an important theorem about modular congruence, which is just this: modular congruence is an equivalence relation. Modular congruence is an equivalence relation. That's a theorem, and we are going to prove it. So Here's a reminder of the definition. If we don't remember modular congruence, we say that A is congruent to B, mod P, if both A and B have the same remainder when divided by P. So let's show that modular congruence is an equivalence relation. So I've outlined our proof here. We need to prove three things. Remember, we want to do an equivalence relation proof. We need to do three proofs. So let's go ahead and prove reflexivity, symmetry, and transitivity for modular congruence. Okay, so for reflexivity, remember that we want to show that for all A in S, A R A, we do not know that yet. That's what we want to prove. Okay, so this means that A is congruent to A mod P. So now that's what we have to show. We have to show that A is congruent to A mod P. This is always true because A and A are the same number. So they have the same remainder when divided by P. So here I could go through a more formal mathematical proof. I could say, hey, let A be any integer. Then I'll prove that A is congruent to itself modulo P. And then I could go through a formal definition there. Here, I'm being a little more casual. They're the same number, so we know they have the same remainder so when divided by P. So that's a little bit more casual, but that's going to be okay for lecture and for quizzes that involve equivalence relations. Okay, so now let's do a proof of symmetry. So this time what we want to show is that for all A and B in the set that I care about, if A is related to B, then B is related to A. Okay, so now let's assume that A is congruent to B modulo P. Then we know that A and B have the same remainder when divided by P. Okay, but here's the thing, that's a statement that doesn't depend on the order. We therefore know that B and A have the same remainder when divided by P. So that means that B is congruent to A mod P, which is what we wanted to show. We wanted to get from A related to B, that was A congruent to B mod P, and we got to B is related to A, B is congruent to A mod P. So this step is also done. Okay, and now finally, and this is usually the hardest one, transitivity. What we want to show is that for all A, B, and C, I have that A is related to B and B is related to C. If that is true, then it must be the case that A is related to C. So let's try it out. Let A be congruent to B mod P and B be congruent to C mod P. Let K be the remainder of A by P. Then K must also be the remainder of B by P. And that's by definition, because I know that A is congruent to B modulo P. So that's by definition. Okay. Now, K must also be the remainder of C by P. And that's because we already showed that K is the remainder of B when divided by P, and we know that B is congruent to C modulo P. So this is also by definition. But now I've proven that A, B, and C all have K as their remainder, which means that A and C have K as their remainder. It's the same. So A has the same remainder as C when divided by P. By definition, A is congruent to C mod P. I started by taking A, B, and C as arbitrary integers and assuming that A is related to B and B is related to C. I did a proof and showed that this assumption would imply that A is also related to C, which I showed here. And so I am done with this as well. And I have proven that modular congruence, so the relation A is congruent to B mod P, modular congruence is an equivalence relation. We've shown this by writing 3 proofs, all 3 worked out, and so I know that modular congruence is an equivalence relation. An important fact about equivalence relations is that they divide up the set that we care about into distinct disjoint sets. So each of those sets is what we call an equivalence class. Formally, definition, if I have a relation that's also an equivalence relation on the set S, I can talk about the equivalence class of an element in that set, which I write using the little brackets around that element. And what the equivalence class is, it's another set. And here is that set in set builder notation. The equivalence class of A is all the other elements of the set that I'll call B here, with the property that those elements are related to A. So everything that's related to A is in the equivalence class. So here's an example. So suppose that ARB means that A is equivalent to B, or congruent to B, modulo 2. Then the equivalence class of 0 is the set of all integers which are congruent to 0 modulo 2. So what are some of these integers? Well, I know that 0 is congruent to 0 modulo 2, but also 2 is also congruent to 0 modulo 2, because when 2 divides itself without remainder. 2 divides 4 without remainder, 2 divides 6 without remainder, and so on. And indeed, I could have gone in the other way as well, -2, -4, and so on. And indeed, if I sort of see what I have here, this is just the set of even integers. So the equivalence class of 0 here is the set of all even integers. Similarly, everything that's related to 1, everything congruent to 1, modulo 2, 1 is congruent to itself modulo 2, 3, 5, 7, and so on, because all of these have remainder 1 when divided by 2. Similarly, -1, -3, -7, and so on. So this is the set of odd integers. A nice way to think about this is geometrically. Equivalence classes partition the set S. Every element of S is in exactly one equivalence class. There's no overlapping equivalence classes, and no element is left out of an equivalence class. And if we draw this, so here's a big kind of Venn diagram type representation of the set S. What this means is that this entire set can be subdivided into a bunch of sets or regions that fully cover S. So here maybe is the equivalence class of item A, here's the equivalence class of element B, equivalence class of element C, equivalence class of element D. So what I'm saying here is that every single piece of S, it lies inside some equivalence class. There's nothing that's outside an equivalence class, and also none of these equivalence classes ever overlap. I can't have that A has the same equivalence class as B unless A and B are members of exactly the same equivalence class. So there's no overlapping here, but there is complete coverage. This is sometimes called mutual exclusivity, no overlaps, but joint exhaustion. Sounds like a medical condition, but joint exhaustion between all of these equivalence classes, we cover the complete set. So when we're thinking about equivalence classes, one way to think about them is as ways of partitioning a set into regions.